Right guys, welcome to the class. So if you remember, in the last class we started the discussion on NoSQL databases, and let's continue that discussion. So in this table you can get some comparison of NoSQL databases versus SQL databases or relational databases. In the last class, if you remember, we were kind of getting some idea about how things are going to be different in. So in relational databases, we store the data in the form of tables, whereas in NoSQL databases, there are so many databases that fall in this category. So that is one of the reasons probably coming up with few chapters just devoted to NoSQL databases may not work. Well, anyway, in this category we have these many possibilities, like some databases can be categorized in this key values kind of. There are some document based, there are some column based, there are some graph based, and even XML databases can be considered as NoSQL. Then the other criteria which we can use to distinguish relational databases from NoSQL databases is whether those are distributed or not. So mostly the relational databases would be single node based. Data is there in one server. Well, it may be possible to have the relational database distributed, but that will really make the life a lot difficult. But these NoSQL databases, they are mainly distributed. Scalability is something that we looked at in the last class, if you remember. Well, what we saw was vertical scaling versus horizontal scaling, and I think that was fine. So in case of the relational databases, it is more convenient to do vertical scaling. Vertical scaling means making our server more efficient in terms of computation as well as data storage. So that is about scalability in relational databases. Whereas interestingly for NoSQL databases, it is very convenient to scale them horizontally. They are very efficient in terms of horizontal scaling, and as goes the kind of systems relational are. I mean, we have some version of relational databases which are closed in the sense that they are not open source. So closed means whether that is open source or not. So I would consider Oracle as a closed system, whereas MySQL I'll consider as open source. Interestingly, NoSQL databases are mostly open source. Now a schema, relational database is schema driven, whereas these NoSQL database, they don't have any strong schema. So these things we will kind of discuss in more detail in the next few lectures. Now SQL is one of the strength of relational databases. It has a well-defined query language, whereas in case of NoSQL databases, seems to me that we don't have a very well organized, very well accepted SQL query language like SQL. Now these things I will touch probably towards the end of the lecture if time permits. The base, right? I mentioned that thing in the last class. So ACID is something we did discuss pretty well, because that is very, very important from relational database point of view. And it was probably in the first few weeks of the lecture. I told you that the transaction, I was defining transaction as a very important program which should satisfy ACID requirements. And there we learned about atomicity, consistency, isolation, and durability. So these things are guaranteed by relational databases, whereas this is not guaranteed by NoSQL databases. And interestingly, NoSQL database, they support base, not ACID base. And now in base they have these terms, which is basically available, soft state, and eventual consistency. So these things are fairly standard, I would say, and easy to discuss. And then, well, these points we will look at later. Let's keep moving. So what we are going to discuss in the next slides today? Well, we will look at the key value kind of NoSQL databases. Now, here we need to understand the concept of key value, and key value, although that is very, very fundamental, so it can be connected to our data structure understanding, and the same kind of concept has been exploited in these kind of databases. We do have the concept of key and there is value. So for key values kind of databases that we'll look into, the keys are going to be unique, and this is very similar to the data structure which is often called dictionary, hash table or hash map. So let's see what we have here. Okay, so a very simple example. The slides are from the textbook, right? So I should not claim that this is something that I wrote. So let's look at it, right? Fairly simple program. And the reason that we have this program in the textbook is kind of, remind you that, what the key value thing that these databases have is so fundamental. So let's look at it, right? Like what this program is doing. It's a program written in Java where we are using hash map and map. And in this program itself, you're creating this age by name as a hash map or map you may call it, and in that we are putting some values, right? So you can think of it as a very, very small database, very, very small, very, what I should say, insignificant kind of one, but it's good enough to understand the concept behind key and value, or keys and values. So once you create this hash map here with the name age by name, then using that you can store some values there, right? So in this hash map that we are creating, which we are calling as age by name, so here our key is going to be the name of people. All right, so we have put 1, 2, 3, 4 records in there, and the way we are putting these records, for that we have our key, which is the name of the person. So Wilfried has the age 34, so we will put that data using the name as the key. Then for the second record we have a different person, Sepe with the age 30, then Bart with 46, with Jean 19, right? So conceptually we are putting the data using the key. Key is the name and value is their age, right? So yeah, that's how we create this hash map with the keys as string and the values being integer. And what we have done, simply use the put function or put method to put these values. And then if you're interested in retrieving that data, you will simply use the get method. Age by name dot get, use any key that you're interested in. Key means the name of the person, and you'll get the age. Okay, so you can print that out. And here what we are doing, we just want to update the value, or rather you want to put another value there, but since there is only one unique key, therefore when you attempt to put a value for Sepe, so whatever its age was, 30, it will be updated by 50. Very fundamental, very basic program involving key and value concept, for which we are using a data structure existing class, you may call it. All right, so now whatever we have done, let's try to understand few very, very important concepts related with key value storage. Okay, so that would involve basically the hash function, right? So what has happened in the previous example, if you see, we are using the name of people as their key, right? So as an example, these are two keys because these are the name of two people, and we did put information about these people as their age. Now in the data structure like dictionary, what we have is a very important concept, that is of hash function. All right, so I don't know, where did I put my pen? Okay, it's right here. So guys, I mean, most of you might be knowing what hash function is, but still it is important, okay, from exam point of view. So what is a hash function? Hash function is very, very important in these kind of storage, because once you have a key, like the key is the name of the people here, what our hash function will do, it will take the key right, which is an arbitrary value of arbitrary size, and it will map that to a key with fixed size, and which is called the hash value, right. So this will be very evident once we take an example. So a hash function takes an arbitrary value. In this case, our arbitrary value is the name of people like Bart and Seth, and it could be of any size, and what it will do, it will map that value to a key which is of fixed size, and that is called the hash value. So you're given something, an input, you apply a hash function, and the hash function will return a value, and that value you would use to store the data. So each hash can be mapped to a space in computer memory. Let's keep it very, very simple for the time being, and using that we can store these values. Okay, so let's look at very simple example that we took. Our key is going to be these values. These are the names of 1, 2, 3, 4 people, and let's assume that we have some magic function, hash function. So we are not going into the detail like how did we map the first name to 0, 1. Let's assume that we have some magic hash function that is doing it for us. So these are the values. Using hash function you got these hash values. Now these are, let's assume, some address of the space in memory, right. So these values that you see are 2-digit integer values. Let's assume that these are some address in computer memory, right. So what we are doing in this simple example, using that hash value to store the data. So in fact, the first person's age, Wilfred, is stored at 0, 1. The second person's age, which is 30, is stored at 0, 3. Bart's value, age 46, is stored at 0, 7, and similarly the last person whose age is 19 is stored at that location, right. So that's what our hash function is doing for us. Fairly simple example. Hopefully very soon things will get slightly interesting. Okay, so now let's move on to hash functions. As I said, right, it's an important concept. So first of all, let's try to understand like what kind of functions one should use and what would be the characteristic of a good hash function. All right, so hash function should have some characteristics, and I'm assuming that most of you people must be aware of these things, because hash functions are usually studied in data structures and probably also in algorithms, but it is worthwhile to have a look at those characteristics. So the first characteristic of a good hash function would be that it should be deterministic. Now what do we mean by deterministic, right? So it simply means that when you have the same input value, then that same input value should always hash to the same output value. All right. So as an example, if you remember in the previous simple example that we had, the name of a person like Bart, which is our key, should always hash to the same memory location. So this is the deterministic criteria. So some very simple hash functions that we can use for numerical keys would be using that value and dividing that by a prime number, and whatever is the remainder we can use that as the hash value, right. So you would see some examples I will be using that modulo function. In other term, we often call that as modulo, right. Whatever key you have, use a modulo, and any prime number, right, like 5 is a prime, and whatever you get as the remainder can be used as the hash function. So deterministic is one of the criteria. What's the other criteria? Let's look at that. Uniform. Now it is important for a hash function to be uniform in nature. So what does this uniformity means? Well, when you are applying that hash function on the key, then the hash function should distribute the value equally in the range, right. So let me read this here. A good hash function should map the inputs evenly over the output range. If that's not the case, then what we will have is called collision, right? So again, these concepts that we are discussing right now are typical data structure concepts, right? So when will we have collision? Assume that we have the hash function h, you are applying that on say two values v1, and the same you are applying on the value v2. If they both result in the same, let's call that k, then this is a collision, right? So we don't want a hash function that would result in too many collisions, right? Now I don't want to go in too much depth of data structures, but the bad news is that collision is unavoidable, right? You will have collision. So if there is collision, probably we'll have to think about collision avoidance and all. That's data structure stuff. But yes, we should have some idea about good functions here. Deterministic and uniform. What's the third criteria over here for a hash function? Well, it should have a defined size, right? So it is desirable that the output that we have from a hash function should have a fixed size, because that will make us that will help us out in the implementation, because then we can think of more efficient data structures. All right, so I thought these were important issues related with hash, so I put these points over here. All right, so now back to the NoSQL databases. If you could remember, right, in the last class also we touched on this point at least, which was about scalability. And in the last class, in 15-20 minutes, or maybe even less, that I could get to discuss NoSQL databases. If you remember, I was of the view, and I still hold that view, is that one of the weakness of the relational databases is the scalability, right? They are not good in terms of scalability. Keeping in view the huge volume of data that applications are handling these days. All right, so one very good attribute or the property of a NoSQL database is that they can scale. And how do they scale? They scale horizontally. All right, so NoSQL databases, they are built with horizontal scalability support, right? So when these were developed, then scalability was one of the issue, and they were designed to scale horizontally. So yeah, these were developed with this horizontal scaling in mind. Now one interesting thing about the hash table that we discussed is that they can also be scaled. So hash table that we have, they can be distributed as well. All right, so let's look into the distribution of a hash table over different locations. So what will happen, we'll be using a very small toy example that we have been using to look into the distributive feature of a hash. Okay, so here you go. Now assume that, it will be very difficult to assume, but let's think that the computer that we had, which was just storing those 4 or 5 names, is too small that it can't handle that, right? So what we have to eventually think about is spreading the hash across different servers. All right, so if our single computer was not capable, let's think about a more what I'll say more skilled, horizontal skilled system, where in place of 1 server, now we have 3 servers. All right, so now let's look into it, like how our hash table will figure that out. So what will happen in this case now, whenever we have to hash a value, like these are our values, like Wilfred, name of the person, say is a person. So initially, if you remember, we had one hash table, right? And we got those values like 0, 1 and all, but everything was mapped to hash table of single computer, single server. Now what will happen here, we will use another hash function that you can think of, which we are calling as index, and that will be on the hash value that has been generated. All right, and how is this function index defined? That is simply the mod of whatever value you had, and then the number of servers that you have. Here we have 3 servers plus 1, right? We are coming up with this, not me, I mean the author is coming up with this hash function, right? So another hash function applied on these values that you have. So once you have this understanding, let's see how the situation is going to change. Here we have it, right? So initially we had only this much of information, right? Like keys were there, we applied some hash function and got the corresponding hash value. All right, and if it was on one machine perfect, right? So earlier we were confined to this much. All right. In fact, you know, this is something that we have added. In the earlier case, we were just putting the values here, right? But now, since we have to kind of understand the distributive nature of NoSQL databases, so we need to think about this case where we are not storing that hash at one server, rather we want to distribute it, right? So we want to understand the distributive nature of the hash table. So for the distributive thing, what we do, whatever values that we have here, right, the hash value that is being obtained, which was obtained in earlier case also by the application of hash, these values, to that we will apply another hash that we are calling as index, which is simply mod 3 plus 1. So if you do that, 1 mod 3, right, remainder when you divide 1, modulo is often used or denoted by the percentage sign. So 1 modulo 3 is 1, that is the remainder. We add 1 to that, right? That is our hash function here. So that will give us the value 2. And here we have 3 servers, server number 1, server number 2, and server number 3. All right. So what is done in the case of the first record which is well-fried, it will be hashed to the server number 2. Here we have it, right? And then for the second record that corresponds to SEPE, whose hash is 03, and you would apply the same index, I mean the second hash I would call it, and it will take you to server number 1. That's where this guy is sitting. All right, so for BART, again, you know, its hash is 7 modulo 3, simple exercise, 2. I hope this is making sense, right? So what has happened here in this scenario, we are looking at the distributive characteristics of the hash table, right? We can easily distribute the hash into different servers. Good. Now, the most important thing is over here, sharding. What is sharding? In the horizontal scaling, what we can do, we can distribute the data across multiple servers. That's what we are doing over here, right? So I should have provided you the definition of sharding probably in the next time I'll do it. But on the basis of what I see in the picture and my background information, when we horizontally scale our data by distributing the data across multiple servers the way we are doing over here, then this is called sharding. Okay, and each data like this one would be called, you may call that shard 1, okay, or the partition, you may also use the term partition for that. The first partition you may call as shard 1, then this is the second shard, that's the third shard, and the whole process is called sharding, horizontally partitioning the data across different servers. Good. Let's keep moving. So in key value stores that we're discussing right now, there are a few things which are very, very important, like request coordination. I'll discuss that soon. Then we will look at the consistent hashing that you may find little interesting and important at the same time. Then we will look at these issues of replication and redundancy. We will have some idea about what eventual consistency is, and this is something that our NoSQL database kind of guarantees, right? NoSQL cannot guarantee consistency, but what it guarantees is eventual consistency. We'll look into that. And yeah, stabilization, till that point I think I will be able to cover today, and after that probably the next class. But before that, let's start with request coordination. So what I could understand, right? So in many NoSQL implementation, example Cassandra, Google's Big Table, Amazon's DynamoDB, all nodes implement the same functionality and are all able to perform the role of a request coordinator. So let me read everything in this slide and then I'll explain. Okay? So fine, this much is enough, I think. So guys, as I could understand, the client is somebody who's requesting data in this framework where we are using key value kind of storage, right? So on the basis of the key, the client may be either interested in storing the information or retrieving the information from one of the server. This is distributed framework. Now, it seems to me that in these systems, as this bullet says, in Cassandra, Google's Big Table and Amazon's DynamoDB, whenever a client is requesting for information either to be retrieved or to be written, it can reach out to any node, and any node is capable of working as a request coordinator. In other words, in these systems, we don't have one node or one server that would take the responsibility of request coordination, right? Every node in the system is capable of working as a request coordinator. And yeah, there's no single node or a server that would work as a request coordinator. Request coordinator, I would assume, is a server that is receiving a request and, you know, taking care of that. Here, every node, all nodes, they are capable of working as a request coordinator. Great. Now, in order for that thing to happen, there is something called as membership protocol. Right? So how come these multiple nodes are in a position to work as a request coordinator? Seems to me that there is one protocol that they are all implementing, and that is called membership protocol. So what I learned from our textbook about membership protocol is that it has two very important components in it. These are dissemination and failure detection. Right? So what is dissemination? Dissemination is the communication that is happening between two nodes pairwise. It's a pairwise communication, and that happens periodically, right? So since this discussion has Cassandra, Google, Big Table, as well as Amazon's DynamoDB all taken together, so these are some general statements, right? So what would be periodic? I don't know, right? Maybe after some time. That could be maybe a few minutes, few seconds, I don't know. But periodically in dissemination, what happens is two nodes on the network, they will communicate, right? And when they communicate, then in the process, they will update their information, right? And interestingly, when I was searching for this information online, right, like what is membership protocol, and then I looked for dissemination, if I could correctly remember, Cassandra has something called as gossip. I may be wrong whether it's Cassandra or not, but there's something called as gossip, right? So the nodes, they gossip. That's an interesting thing actually. So the point is, since it's a distributed system, every node is capable of resolving the request. Every node is working as a request coordinator. Another point is every node should know the status of the network, right? Now what are the possibilities? Well, there could be a lot of possibilities. So one of the possibility would be, like, let's assume that everybody who's sitting here is a node, right? So now in my lecture it is possible that someone might sleep. Happens in lectures, right? So another point is everybody should know whether the other guy is awake or not, right? And how many people are paying attention to the lecture. So it's the same thing, right? There are servers. We want to make sure that servers are still alive. Servers are still coordinating, okay? So what will happen? Randomly, two people will probably communicate with each other, right? Like out of 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9. Out of the 9 students, how many students are still awake? That kind of a thing, right? So it is not multicasted. That's what I'm trying to explain. In this system, we are not letting every node send the information to every other node. Right? You know what? I'm still alive. I'm still listening to the lecture. Because that will make it very inconsistent, right? A lot of traffic could be used. So that is avoided. It's not multicast. Every node is not simultaneously informing other nodes that we are alive. Just two nodes at random will come alive, not come alive, will communicate with each other, and they will gossip. Again, I'm not using the term gossip, but yes, they do the same thing, right? Let's assume that one node here and one node there, they for some reason came alive and they gossip. Then what will they gossip? They will share their status information, whatever they know, right? Like this node, say 5 seconds back, had this information that 5 students are still listening at 5 seconds back, whereas the other node is saying 10 seconds back, 7 students were listening, right? So what this node will do, will update its information, right? So ultimately, in dissemination part, that is how through the means of pairwise communication on a periodic basis, the whole network information is stored in different nodes, right? So the nodes, they will know about the status. Is that making sense? I know, it's not too much, but anyway, that's what I could find. It's a gossip thing, right? So through the gossip, you'll know about what is going on. All right, so yeah, the nodes also, they gossip, and through gossip, through the dissemination of the information, and that happens between two nodes at a time, right? Then other two nodes, then other two nodes, right? Probably at some time, the whole network will have some information about the other nodes, okay? Great. Now, in this membership protocol, we have another part which is failure detection. Now, question is, how will the failure be detected? Failure means out of the 9 students, say 1 student is sleeping, right? How can I know whether a student is sleeping or not, right? If I ask a question to the student doesn't respond, that means student is sleeping, right? Or maybe from you people, right? You try to reach out to the other person to gossip, right? And it so happened that the other person did not respond to your gossip. That means that guy is sleeping. Now you will probably reach out to another person and say, you know what, I reached to the person X and that person is not responding. Seems like the person slept. Right? So that way the failure is detected. Probably there is more detail to it, which unfortunately the textbook does not cover. Making sense? Now you have the scope of writing a lot of stories. If I ask you this question in exam, feel free to do that. Okay? All right. So now here storytelling will not help because we know what is consistent hashing. So consistent hashing are the schemes which that are used very often, and that they avoid the remapping of each key to a new node when the nodes are added or removed. All right. So now this is going to be interesting here. Guys, if you remember, I did say that multiple times that the strength of the NoSQL databases over relational databases is their horizontal scaling. So what will happen? If the need arises, you will add more servers, right? And when you're adding more servers, the chances are that some servers may die as well for a lot of reasons, right? So now, if you remember, we looked at a hashing example, and then the hashing was thought about in the framework where we have multiple servers. Then the hash table was distributed across servers. Now let's think about the scenario where we may add more servers or we may remove some servers, right? So what will happen to hashing? Okay, so simple scenario, right? Let's assume that we have 10 keys. Now it is a little mathematical, right? More objective, I would say. Suppose that we have a situation with 10 keys and they are distributed over 3 servers. N is going to be 3, and I think for keys you can use the symbol K. We have 10 keys that are to be distributed across 3 servers, and our hash is a different one. That is key, okay, let's call it key modulo n, right? So earlier, in the early example, we were using key modulo n plus 1. Here, in the example that will follow, our hash has changed. Just to make it a lot simpler, we are simply using key modulo n, where n is the number of servers. Good? So let's see what has happened. Now, you need to pay attention to the first column over here, right, which is fairly simple. We started with n is equal to 3 servers. These are the different keys from 0 to 9. There are 10 keys, so they can get these index values, right, 0, 1, 2, all the way till 9. Now, the point is, if the key is 0, to which server will we hash? So, you know, so simple that you would remember key modulo 3. So, 0 is being hashed to 0th server, and 1 is being hashed to the first server, and 2 is being hashed to the second server, server 0, server 1, and server 2. These are the server IDs. Fairly simple. When you have the key value as 3, you do 3 modulo 3, the result would be 2, which will hash the key 3 to server 0, so on and so forth, right? Fairly simple computation, you can do that. And after doing these computations, you will figure out that, you know, by using k modulo 3, we can distribute the keys to these 3 servers, server 0, server 1, and server 2. Now, let's think about the case where one of the server dies, right, and we are left with only 2 servers. 2 servers are dead, right? So, what will happen here? In fact, key modulo 3 that you are using should have been key modulo n, where n is number of servers. So, when one of the server has died, let's think that we have only 2 servers, server 0 and server 1. All right. So, what will happen with the same keys? We will try to remap, and remapping is important, right? Because you know what happened. Very simple example here. Let's assume that one of the server died, and you had stored or mapped those keys like 2. Let's look at this key value 2, right, which was earlier mapped to server 2, but the server 2 is dead now. So, what you should do, you will have to map it to a new server, so that later on when somebody is requesting for this information, we should be able to retrieve it from a new server now, right. So, this is required to be done. So, look at it, this is in red for the reason that earlier key that was hashed to the 3rd server, which was server 2, now it should be hashed to server 0. Good. Similarly, for the next key also, which is 3, it should be now remapped to the server number 1, which was earlier mapped to server 0. Same thing is happening with other keys as well, right. So, these red entries that you see are for the reason that here we will have to do remapping. Good. Now, let's move on to the case where we have one more server, right. So, whether you are reducing the number of servers or increasing number of servers, you need to remap the keys. Okay. So, when you are remapping the key with n is equal to 4, look at it, what happened. For this it did not change, for this it did not change, for this it did not change, because now n is equal to 4, right. But this guy, which was earlier hashed to the first server, server 0, needs to be hashed to a new server, server 3. Similarly, 4 will be hashed to 0. Fairly simple thing which you can easily do, just the modular thing. Now, what is this whole picture trying to explain? Just one point, that is this kind of hashing that we have done is not good. All right. So if you're somebody who loves mathematics, and I love a little bit, then here is the expression. So let's look at it, right? I did not derive, I did not go to that extent. I just borrowed this expression here from the textbook, which says that if from initial n number of servers, like if from initial 3 number of servers you went to 4 servers, then how many moves you had to do. So that can be evaluated by this expression, 1 minus n divided by k. N is the initial number of servers that you had, and k is the total keys that you had, right? So if you put the values here, then 1 minus initial servers we had 3, the keys we have is 10. So if you work it out, it is 7 by 10, which is 70%. You can count 1, 2, 3, 4, 5, 6, and 7. So 70% of remapping we had to do when there were initially n servers and the number of keys were 10. Now let's think about a case where we have 10 servers and there are 1000 keys. So it boils down to 99%. Extremely inefficient, right? So these numbers are just establishing the fact that this hashing that we are doing is inefficient. And guys, don't get misled by this thing, right? It is not consistent hashing. This is normal hashing. Consistent hashing we will see very soon. All right? So we need a better solution, and that takes us to the consistent hashing. All right, yeah. So in the consistent hashing, we use a different kind of topology. You are looking at a 1, which you are looking at that topology, I think, right? It is called the ring topology. And what it does, it represents the number in the range from 0 to 1 in our case. In one of the very interesting video that I was watching just before the lecture, that seemed to be by somebody who was preparing students for interview. And that guy had even interesting example. I did not have time for that, so I will stick with what we have from the lecture slides. So guys, let's look at this ring topology, right? So here we have kind of divided it evenly into 1, 2, 3, 4, right? It's an ideal case where every position is mapped to some number. So position 0 is mapped to value 0, and position 0.25, which you may call as the second position, then third position, fourth position. It makes a lot of sense here, right? These positions have been obtained uniformly across the ring. All right. Now, what's the intention of this whole thing is to kind of find the position of the servers on this ring. All right. It will make a lot of sense once I take you to the next slide. But let me make sure that I have not missed anything. Now for the consistent hashing, this is now consistent hashing. Its central idea, the core is in its topology, which is ring topology, and which is basically a representation of number in the range 0 to 1. Good. Now let's look at it, right? Now it will make a lot of sense to us, and we will be able to map it to the example that we had. All right. How did we put the servers in these positions? Doesn't look like evenly distributed, right? In this case, we picked 4 evenly distributed positions, right? Just to understand how this ring topology will help us out. But here, if you look at, we did put servers in 3 locations, right? We are not using modulo thing over here. That modulo is thrown out of the window because that was not consistent. We came up with this expression also that gave us 70% and 99% thing. Now, can anyone guess? Look at their values, right? For the server 0, it is 0.11. Server 2, 0.27. For server, it is consistent what? Consistent hashing. So there is a hash function which is helping us in positioning these servers. All right. So by hashing, the server 0 was put in this position, right? That will correspond to number 0.11, and then server 2 corresponds to number 0.27. Server 1 has the position 0.58. So every point in this ring that you have will have some value associated with it. Okay, fine. So we use the hash function, we put the servers in these positions. Now let's say that we have the key value 3, right? If it was modulo 3, you know 3 modulo 3 is 0, it will go to the server 0. But this hash function that we have, interesting one, consistent hashing will have its own hash function. It returned the value of 0.78 for 3. You put this some magic function, right? We don't even know about it. So when you did h of 3, it gave us the value of 0.78, and we know where 0.78 is situated in the ring, and here you have it, right? It makes some sense also, right? If you look at these values, so 0.78 is in between 0.58. This is increasing in this order, if you see. All right, yeah. So it will be hashed to this position on the ring. Now the question arises: fine, this is a key. It should be placed in one of the server. Now, which server should we assign to this key using consistent hashing? So the answer to that is that each key, okay, hash each key to a position in the ring, like key 3 has been hashed to 0.78, and store the actual key value pair on the first server that appears in clockwise of the hash point on the ring, right? So you got it this way. You can't go the you have to move only in the clockwise direction, and in your move in the clockwise direction, you have to put this value in the first server that you encounter. Got it? So key 3 will be saved in or will be assigned to server 0. All right. Now the question arises: how come that is going to help us out, right? Consistent hashing is supposed to be better than the modular hashing, right? That's the whole idea behind this discussion. Okay. So for that, let's keep moving. Now what will happen here, where we are relying on the hash function. So because of the uniformity property of a good hash function, roughly 1 by n of the key values pairs will end up being stored on each server, right? Let's assume that the server that we are putting are equally distributed, like this ideal scenario. Server 0, server 1, server 2, server 3. All right, 4 servers. So now you can see, right? Look at it. These regions are equal, right? This one, 1/4, 1/4, 1/4, 1/4. So if you are using a very nice hash function that will uniformly distribute key around this ring, then we are fine. Each server should get 1/4 the keys, right? Okay. So most of the key value pairs will remain unaffected in case a machine is being added or removed. So this is a point that we need to investigate. The claim is that in this consistent hashing that we are learning, if some servers are removed or added, then these servers are not going to impact most of the other servers, right? So let's look at that claim. So for that we have a picture over here, right? So in this picture, what are we doing? Server 0 was already there at 0.11, and server 2 was at 0.27, nothing changed there, and then yeah, server 1 was probably at 0.58. Yeah, these servers were already there. Now let's assume that we are introducing another server here, which is server 3, right? And how will the server 3 be placed on the ring? Hashing, right? Whether it is a key or a server, everyone would be hashed. Okay, good. So yeah, so the server 3 was hashed to 0.75. Now let's think about it. Okay, so first of all, when you put the server over here, what should you do after putting the server there? Do we need to remap the keys and values by putting one additional server? Did we do that in that modulo hashing? We did in the modulo hashing, right? We will have to move. So these red entries that you're looking at, we have these red entries because we had to move some keys to a new server. That will still have to do, but probably what we'll do here would be much less. What we'll do in consistent hashing would be much less than this one over here. All right. So here in this example, if you remember, we ended up moving 70% of the keys. Extremely inefficient when we have just increased one more server and there were only 10 keys. Now, in this case, we will have to, right? So what will we do? If you remember, initially, when we did not have this server, right, then whatever was being generated here, that went to this guy, right? Okay, so what we have to do in this case, we will have to do remapping, but the remapping will be based on all these keys that were generated in these regions, right? Because now for these keys, we have a new server, right? So these keys which were put on this server, they need to be put on this guy over here, right? So only for this region, only those keys that were mapped on this region, they will have to be remapped again. Am I making sense? Right? The remaining keys which were, generated from this part to this part, and this part to this part, and this part to this part, they would remain unaffected by this new server being introduced. Make sense? Right? Yeah, so that is an advantage of this consistent hashing. All right? All right. So if you are somebody who loves math, then here we have it, right? So in this case, the number of keys that you will have to move, for that again we have an expression which is k. K means the number of keys that we are handling, n plus 1, n is the number of servers that we have, that we earlier had, and we increase that by 1, n plus 1, and you can compute that, right? Now let's look at few more issues related with consistent hashing. So we should not be very happy with the consistent hashing that we have seen, because the version of consistent hashing that we saw has also some potential of issues, right? So let's look at that. So now we will look at the problems that may arise with the consistent handling that we have just discussed, right? So what are these? If two servers, they end up being mapped close to one another, then one of these nodes will end up with few keys to store. Is that making sense? Right? Let's go back. If in place of putting this guy here, if I put this guy only up here or another server over here, then look at it, only these keys which are mapped in this region, they'll be stored over there, right? Okay, so this could be a problem. If two servers, they end up being mapped close to one another, one of these nodes will end up with few keys to store. What's the second point? In case a server is added, all the keys moved to this node originate from one other server. Is that making sense? Right? So yeah, these are some challenges we'll have to think about. So what is done? The solution that people have come up with is that instead of, that's very interesting actually, instead of mapping a server S to a single point on the ring, we map it to multiple positions which are called replicas. Okay? So just to ensure that the servers are getting fair distribution, so what we will do, we will have some replicas introduced, and each physical server S will end up with R number of replicas on the ring. So let's look at it. And wait a second, let me finish all these bullets and then I'll take you to the picture. Note that each of the replicas will still represent the same physical instance. So the question of redundancy does not arise. Okay, it's just like this, we are playing some game, right? So what I'll do, I'll say, okay, fine, I will buy multiple locations, right? So this is also my chair, this is also my chair, that is also my chair, right? So similarly, every server that will have multiple replicas, right? Something like this. All right. So what do we have here? Look at server 0. Well, there is a typo here. It should be 2. Server 0, replica 0, server 0, replica 1, and server 2, replica 0, server 2, replica 1, server 1, replica 0, server 1, replica 0, server 1, replica 1, right? So in this version of the consistent hashing, you can see that we have multiple replicas for each server. Well, in fact, this is a different example, but we can use it for understanding this replica as well. And these replicate each, note that each of the replicas still represent the same physical instance, and which are called virtual nodes. So the replicas can also be called virtual nodes. Good. So with that replica virtual nodes, we can overcome the problems that might arise because of the basic consistent hashing thing. Now what, in case of the NoSQL databases, we have another advantage, right, which is achieved by redundancy. So if you want to have the redundancy in your distributed database, which I believe you should have, then how to achieve that, right? So do you agree with me? Should we have data redundancy? Does that help? Okay, how about it? When we are discussing normalization, do we need data redundancy? No, right? Because in normalization, we wanted to get rid of redundancy so that we don't have the problems because of anomalies, right? But when we are thinking about a scenario where our data is going to be distributed along multiple nodes, multiple servers, we need to take care of the problems that might arise because of the failures of some servers or the node, right? So for that case, we should have some redundancy. Now to handle the data replication or the redundancy, many vendors of NoSQL databases, they have extended the consistent hashing mechanism so that the key value pairs are duplicated across multiple nodes, right? So what was this picture saying? Well, when you have this new key, right, then what you would do, you would store this key not only on this server, you will have this in the other server as well. All right, just to make sure that it is consistent. So to handle the data replication and redundancy, many vendors, I already read that. Okay. So by storing the key value pair on 2 or more nodes clockwise from the key position on the ring. Okay. It is also possible to set up full redundancy scheme. So this picture is about full redundancy scheme where each node itself corresponds to multiple physical machines and each storing a full redundant copy of the database, right? So server 2 has been backed up to 2 servers, whereas server 2 replica 0 and server 2 is replica 1. It's making sense? Eventual consistency. The SQL database or the relational database works on ACID, and in ACID one of the term is consistency, right? The consistency there is slightly different from the consistency term that we use in NoSQL databases, right? So consistency in case of relational database means that our database that we have, the state of the database satisfies all the constraints that we have set up. when we define the database, right? So the data that we are keeping in our database should satisfy all the constraints. That is the consistency in relational databases. Here, in terms of here when we use the term consistency in NoSQL databases, then it means that since we will have redundant data, right? We will have redundant data, right? Distributed data, we will have some redundant data. We want to make sure that the data that we have in one node and the same data if we have in the other node, they should be consistent, right? It is possible that they may not be consistent, right? And this scalability in NoSQL databases has been achieved by relaxing on the requirements of relational database. Okay, so in NoSQL, what we want is eventual consistency, not immediate consistency. That is not achievable, right? So the flexibility that we are achieving, or the scale that we have achieved in NoSQL databases is coming with a cost. One of the cost is inconsistency. We don't want immediate consistency. We can't have that. So in NoSQL databases, we are happy with eventual consistency. Over the period of time, the database will be consistent, right? But we can't guarantee that at every moment. Okay. So back to the membership protocol. If you remember, gossip thing, right? Gossip I discussed in membership protocol. Membership protocol does not guarantee that every node it will be aware of every other node at all the time, right? So while you are attending the lecture, some of you might be sleeping. That is all right. I want some students to pay attention so that I don't sleep, right? Just trying to make it funny. Well, so that's what it is, right? If in the whole system we make every node to be consistent, it will not work, right? So the end of the dream of NoSQL. So therefore, we try to arrive at some level of consistency. Okay. So the membership protocol, if you remember, the gossip thing that we are doing, that gossip is happening between two nodes, right, pairwise, and then maybe those nodes are busy with their own business. Okay, so it does not guarantee that every node is aware of every other node at all the time. It will reach a consistent rate over time, right? So eventually it will be consistent, you know, very optimistic. Now, the state of the network might not be perfectly consistent at any moment in time, though will become eventually consistent at future point in time. Okay, and then let me see what I can do. Probably this would be the last point. Many NoSQL databases guarantee so-called eventual consistency. Okay, what next we have? A base is something we will discuss later. So let me stop right here. I'll see you guys in the next class and probably we'll finish this.